Okay, hello again. Good to see such a large turnout for this event. My name is Karo Afiegbe. I'm the Technology Enablement Manager here at CRIN. And just before we kick off, we need to acknowledge the land in which we're having this event. So as we all know, acknowledgement of the land is an important step towards reconciliation. Today, as we are gathering from across Canada, please take a moment to recognize the land where you reside and work. This event is being hosted from Calgary, where we acknowledge and pay tribute to the traditional territories of the peoples of Treaty 7, which include the Blackfoot Confederacy, comprised of the Siksika, the Piikani, and the Kainai First Nations, the Tsuut'ina First Nation, and the Stoney Nakoda. The city of Calgary is also home to the Métis Nation of Alberta, Districts 5 and 6. So a few housekeeping items. We have the men's washroom on my left, just halfway down the corridor. There's a standing sign there. Then the women's washroom on my right. You will need a key card for the women to access the washroom. And please, if you haven't signed in, kindly go back to the reception and sign in so we can account for those who are here. And we appreciate those who have come in online as well. So just a very quick overview of CRIN. So CRIN stands for Clean Resource Innovation Network. And essentially it's an organization that is established to strengthen the network amongst organizations that target addressing emissions from the big emitters and small emitters. And what we also do is to enable technologies that fulfill the expectations of adopters to cut back on emissions. So as a result of that, CRIN fosters 7 theme areas that we want to apply our resources to, and in some cases funding. And when you think about our environment, the air, the water, and the land, and the extraction of resources, they all fall into 7 theme areas that we have developed. So these areas are carbon capture and value-added products, methane abatement, getting clean fuels for our cars and the planes, managing the use of water in our industry, our land use and remediation, the use of advanced digital technology to address all these theme areas. And of course, we are here to look at ways to extract hydrocarbon in a novel way. So at this point, I would like to invite Claude Gaza from Alberta Innovates, who would kick off and introduce the next part of this event.
Thank you so much. Good afternoon. It's good to see a good-sized contingent here for this talk. As Aro said, I'm Claude Gazar. I'm with Alberta Innovates. We are a provincial grant funding agency that supports technology and innovation, delivering on the province's mandates. I'm joined here with a couple of my colleagues, Dr. Murray Gray and Bruce Duong. I get the pleasure of introducing our speaker for this afternoon, Alex Filstein. He is the CTO of Watercut Inc. He's an expert in SAGD and solvent technologies. He's previously led technology projects for Cenovus and ConocoPhillips. He holds numerous patents and publications, specializing in thermal in-situ production optimization and green technology integration. He's also pioneered the COSIA Pathways Solvent Consortia and served as a board observer for General Fusion, Hi-Fi Engineering, and Saltworks Technologies. He's been the recipient of 2018 Oil Week June Warren Rising Star Award, 2019 University of Calgary Technical Achievement Alumni Award, and a 2024 ConocoPhillips Global Spirit Award. He is also an author of a book called Apollo Autism, which supports autism families, and he also enjoys supporting SAIT's petroleum engineering program for the past 13 years. So if you would join me in welcoming Alex put your hands together. Thanks.
Thanks. Nice introduction. No pressure. Lots of familiar faces in the audience, so thanks so much for coming. Really appreciate it. And lots of people we collaborated over the past almost 20 years here, so good to see everyone. So today I'll talk about using solvents to improve SAGD operations, lower SOR, and boost sustainability for oil sands development. And we published a paper during my time at ConocoPhillips collaborating with Inutech Alberta. This is the number for this paper, so if you guys want to take a note of that. I'm not going to cover the paper. It's going to be more like 2.0 plus plus, more updated version of what we discussing in this paper, and providing more kind of insights to what's going on right now, because people want to know what is this all about, how come some companies commercializing this technology, and where we currently stand. Okay, so of course the most logical thing is to talk about vending machines, right? And you get a bag of chips, you get stuck, so you can see it right there. You pay for another bag, try to dislodge the first one, and this happens right there. So what do, right? You ram into the machine, maybe. You get another one. I really like that solution, because it makes you wonder, is it gonna like just elevate the other two bags, or? Yeah, exactly, right? So, or you can start kicking. And if we think about this as a reservoir, you could put a coin, and then you want a bag of chips. But in the case of solvents and reservoirs, you want the coin back as well, okay? Here's another example. Food stuck in the airport vending machine. Some comments here. You get the peanut M&Ms and problem solved. Maybe, we don't know. But somebody became kind of innovative from that aspect, saying, well, there should be a bar you can slide up the vending machine to knock loose stuck items, because maybe it just happens often. And so if we think about the previous example, here we have somebody that's trying to think, okay, maybe there is a system we can develop to avoid all the scenarios in the future. And again, within the context of those reservoirs, a lot of us in the space tried optimizing solvent recovery in addition to oil production. All right, so let's talk about what solvent's all about and how it fits within the SAGD picture. But first, we will cover the SAGD technology. So SAGD is steam-assisted gravity drainage. And today, this industry is absolutely huge, huge. We produce today about 1.7 million barrels doing that, okay? 1.8, 1.7. The core idea here is that our oil is essentially like a hockey puck, and it's very deep underground. So we inject steam to heat transfer it to the oil so we can produce it by gravity. So that's the core idea. The inventor of this technology is Dr. Roger Butler, which back then worked for Imperial Oil. And here you can see he's doing some kind of vessel there with pressures. It's ironic that actually Imperial didn't implement SAGD at that stage. And we actually, at times during my career, we got some pushback, like how the solvent technology takes so long to develop, right? But his work was in 1978. And I would say we commercialized SAGD, I would say in late 90s. Like full-scale commercialization was maybe Foster Creek, my former management, during Encana days, commercializing PAD at Foster Creek and kind of bringing that online big time with a lot of optimization. And so 20 years from 1978 to 1998, now we're 2025, I would say 20 years of technology development, and we do see commercial cases today, and I will share those as well. The SAGD technology also was optimized over the years from a completions perspective. I talked just recently to a gentleman here that's doing VIT, vacuum insulated tubing, but there's a lot of kind of attempt to optimize SAGD. As you can see, we go deep underground, and the wells are fairly long. They could be 800 meters long, it could be 1,000 meters long. The pay of the reservoirs, as you can see in this picture, could be as high as 30 meters. So my height is 170 something. So then times 10 is 17 meters, and times 2. So those reservoirs are absolutely huge. That's why it's called low decline, low cost, because It takes years and years, sometimes decades, to develop those reservoirs. But from completion's point of view, significant effort in the casing, control devices, outflow, inflow control devices, electric submersible pump, and really controlling kind of like utilization of steam to control better SOR performance, so steam to air ratio. Typically, when we talk about solvents and SAGD comparison, you will see something like this, okay? So when technology developers, corporate technology developers will go to management, they'll say, we have a base case, which is SAGD, so oil rate below. This is a simulation case, and we can boost that oil rate. On a cumulative basis, you can see below kind of relative performance, and SOR will always be lower. But why? Some companies, so this is from 2014 SAGD for Imperial Cold Lake simulations. But why? Because steam to air ratio here, you can reduce the S, right, the steam, or you can improve the oil and maintain the steam. So there's like two angles to that. And we're going to cover who does what and what technologies are kind of practical. But of course, you want to uplift oil production and maybe reduce the enthalpy of steam utilization. So this is a little bit more like relative heights, right? So this is from 120 years ago at the Basca River. This will be the steam chamber if it was underground, 5-meter distance between injector and producer. And the height of this reservoirs, as I mentioned, could be 25 meters. Saskatchewan, they're like 17, 20 meters. We have steam chambers in Alberta as big as, in height, as big as 40 meters, right, for some assets. But reservoirs fairly homogeneous. Okay, so going back to the vending machine example, inject a coin, get a bag of chips, right? So here, basically, we inject steam. In our case, we produce the condensed water that transfer the heat to oil to be produced by gravity. We handle the emulsion at the back. And the coins here, within the context of solvents, is kind of like, yeah, I already spent money to inject that steam, but now I have to spend more money to generate that solvent and inject it. And now the expectation that I produce it back because it's very valuable. And those reservoirs can be very heterogeneous, right? So the steam chambers could be very different in shapes, have different pressure gradients, different temperatures as function of those geologies. And so guys like me in the past would simulate that and kind of come up with a strategy on how you inject solvent, how you utilize recovery scheme, how you boost production, and reduce emissions, essentially. Okay, so this I stole from Engineering Design Fair from UFC, but from what I remember, this is legacy and Kana slide for steam chamber development. And really to explain the science of this, in the first stage, we preheat the injector producer region so we can create communication here, right? Because you can't really produce the oil if there's no communication between injector and producer. And a lot of us in the space that innovated in the space tried to come up with timing on solvent injection. When is the optimal time to inject solvent? How do you recover it faster? What solvent would you use? And so a lot of kind of that rising steam development on the lateral scale, a lot of us were kind of innovating in that space. Why do you guys think this is very important point? Because every heat transfer for steam up to this point is heat transfer to produce more oil. But once you reach the overburden, now you have heat losses to the overburden, right? So you need to minimize those and expand the chamber growth so you can recover the oil. And the exercise, we use complex equations of state like Payne-Robinson, other equations of state. But here's a very simple one. PV equals nRT, ideal gas law. So pressure, very important in reservoirs. Volume, you need to inject more steam over time. So how do you mitigate that? Amount of substance N and T temperature, right? So one of the kind of disadvantages in thermal processes is that it's thermal, that you need to inject a lot of heat. And you can see on the picture there, those chambers become different in shapes, right? So you need to mitigate that. Okay, let's explain the science of solvents. If there was one chart to understand, this would be it. This chart will explain to you LNG. This chart will explain CO2, CCS, solvents, SAGD, among others. So let's say you go to your friendly a gas station to get barbecue for propane for barbecue, right? So that's the yellow star. In the bullet, the propane will be liquid. It cannot be gaseous, right? Because storing gaseous propane will be very expensive. So this is the vapor liquid equilibrium curves. My former professor, Dr. Gates, wrote a paper. I really like that chart to explain that. So if you look at the yellow star here, this will be propane right here. On the right side of this chart is gas, vapor. Left chart is liquid. So to meet the vapor pressure conditions in this bullet, propane has to be at roughly 1.3 MPa. Do you guys see it? Right? Very easy. Once you start barbecuing, you drop pressure, you go down, straight line, you release pressure, it becomes gaseous. Okay, LNG, those tankers, very popular topic these days. Same science, but on the temperature side. LNG, liquefied natural gas, is basically methane. Over 90% of it is methane. And that cooling will be at 100 minus 163 degrees, something like that, minus 64. So that's the vapor pressure condition, right? And you can see the challenge with methane and how difficult it will be to bring it to condensation, to liquid phase. Same thing with CO2, right? Carbon capture. Why we go so deep underground to liquefy CO2? Because you need about 10 MPa to bring it to liquid phase. So that will be this chart here. Okay, so now we're talking about SAGD. That will be the blue star here. And the idea here is to reduce the enthalpy, to reduce the energy intensity, to improve the SOR. So now you have to move to the left, right? To reduce steam and energy associated with SAGD recovery. Which brings me to the red star as an example. For example, this will be butane. So, and you can see kind of the relative performance there. And why butane in this case is because it's soluble in oil. Butane is oil. Just like methane is the lightest version of oil under certain conditions. It just happens to be gas naturally, so we call it natural gas. So the idea here is, what do I co-inject to improve the SOR? So that's really the science of solvents. Okay, so C30 plus test, and you can see it's in yellow. This is really the composition of the diluent. When companies say we inject diluent, this will be that in yellow. So that will be condensate, diluent, hexane, pentane composition, C30 plus test. The test we use is called SIMDIST, simulated distillation. In the past, I worked on C3, for example, which is blue. So you will see over 90% is blue for propane, and C4 butane will be green, but you will see it in the SIM test. And that's what we co-inject with steam. And obviously you will have the recovery scheme will be injection well casing, same as SAGD, and you're trying to kind of create that condensation. Why does it work? Because the hot solvent vapor being injected, but the temperature here is about 10, 12 degrees on the sides of the chamber. So if we go back, we're shifting the curve to the left, so now we have to condense, right? So that's really the science. And the exercise is reduction of viscosity, which is a function of temperature. And you can see viscosity temperature relationship that shows virgin conditions for viscosity for Athabasca and Coal Lake, which can be close to 10 million centipoise. And as temperature increases, we're able to reduce the viscosity of the oil so it can be drained by gravity. Some people could say, why don't you just frag the sand? Well, assuming it's a hockey puck, guess what happens to a fracked hockey puck? It's still a fracked hockey puck. It can be drained because you need it to be in liquid phase. Okay, so now we have various types of projects in Alberta. On the left, and I used it for January timeframe this year, CNRL Kirby North. It's 30,000 barrels per day. ISOR instantaneous was 3.5. And on the right, we see about 240,000 barrels a day for Christina Lake. SOR instantaneously was about 2. Okay, so in my daily life, I interact with lots of finance guys. You know, right now we have this transaction between Strathcona, maybe it's Novus, Med. They're talking about whether they're going to be getting shares or equity or cash, right? But people don't talk much about the SORs, the efficiency of steam utilization for those assets. And the lower the SOR is, the better it is. The lower energy intensity there is, the better utilization, and you can expand with more steam, basically doing more with less. And that's the idea. How do you basically create that the trick? From CNRL, it's another opportunity to maybe integrate, and that's kind of what they're doing right now in Kirby South, after Kirby South pilot, integrating solvents in Kirby North, and soon we're going to be seeing from their public slides. I guess the key message here is that those SAGD assets are very different. This is from Athabasca Hanging Stone, downhole. Now we're going deep underground, and you look at this design and you think, okay, if I was to inject solvents, how would I operate those pads? Because if you have coalescence of all the steam chambers, what talks to what? Where do I reduce pressure? What's the strategy, right? And you can see the average interval spacing, for example, in their case is about 100 meters, 25 meters in pay. And then in length, you have wells are 700 meters, 600 meters. But I guess this is something to think about, like how do you operate something like this, especially when you want the solvent back. By the way, they don't do solvents in this asset. They do in-situ co-injection, so non-condensable gas co-injection. Okay, so let's talk about oil prices. Whether we want it or not, very volatile oil price sector. Great financial crisis here. Oil glut, Saudi oil glut here. Lots of people really scared that it's going to happen this year, maybe next year. Minus 37 right there at the bottom. Ukraine, Russia attacks Ukraine there, 120, and we've been slowly decaying in this price environment. So there's me there at the bottom, and Bruce, where are you? Okay, I think that's you right here. That's you, that's Brian, Vanessa, Natasha there. We just trying to operate, collaborating together, trying to operate solvent, not knowing that we're going into COVID, yeah, and coming out of the oil glut here. So economics change a little bit. And then this picture here shows basically the OPEC spare capacity. And we've seen times where OPEC spare capacity declined and we saw higher oil prices. We saw times when OPEC spare capacity increases and we saw lower oil prices. So I would say there's maybe very little correlation when it comes to that. But I'm really showing this chart because from a technology development point of view, it's kind of tricky, right? You're kind of challenging the status quo here. You're trying to do something meaningful, but it's extra spend. So that's why I believe collaboration with governments, academia is very important in this space. Okay, so this is from one of the patents I worked on in the public domain, and you can see correlation between spot prices for hydrocarbon, gas liquids, natural gas, crude oil for the past 20 years. And there is very huge correlation between the prices of propane, butane, and crude oil. So now, within the context of you put a silver coin inside, you want to get a gold coin, but you also need a silver coin. How do you mitigate that? How do you take that risk, right? WCS differentials, huge, right? We don't get WTI prices in Alberta, we get WCS. Those spreads are pretty good for this year and last year because we have the TMX expansion, which is awesome. But there were years in the past where this delta was as high as $30. And so you basically could get squeezed on the butane side or propane side, where everything converges basically to zero during a drop like what we've seen during COVID. So the gold coin becomes gold coin, and then you need the gold coin and 2 coins back, and the silver, you need everything back. Okay. By the way, we're going to have time for questions afterwards. So companies have opportunities to allocate capital. That's just the real world. That's how it works. So in this price volatility environment, what we see today is debt reduction. We have very clean balance sheets for many companies. Some of them are debt-free. Buybacks is a huge one, okay? Dividends, we see some M&A in the space. And then the other way to allocate capital is R&D technology. So I would say there were like lots of cyclicality in those, in this business when it comes to experimenting. So just want to provide this as a background. Now, I want to talk about Imperial Oil a little bit from the public domain. Imperial Oil is an intriguing company. Obviously, kind of sad news recently, but nevertheless, stock price at all-time high, okay? And guess what? Look at this chart, the yellow chart. So this is buyback have been the most tax-efficient capital return factor for cumulative returns of different S&P 500 factor net of taxes. So historically, when companies buying back shares, they're able to support the price through volatility. So when there is no incremental buy, when the company buys their own shares, there's this inherent advantage. For example, gold today is like 4,200, right? People buying gold, people buying NVIDIA. So not too many people think about oil companies at $58. But companies are busy buying back shares, which is great. So this is something to keep in mind, but at the same time, they're commercializing solvents, which is good. I want to talk a little bit as a background to something that maybe initially looks like a bad investment, but very applicable to today when it comes to technology development. So knowing what we know about oil prices, this is from Ag Energy, okay? So you have 4 billion OBIP, so original bitumen in place in development area, in project area, about 2.2 development area, billion barrels, which is huge, right? And combined active well pattern, 0.89 billion. And now recovery factor is about, I would say, this is as of year-end 2023. I would say cumulative recovery factor on the development area right now is about maybe 11, 12%, meaning there is another 88% of oil to still go for the next 30, 40 years. And this is their development area there. Now, you go into the oil glut 2014 to 2020, and look what happens here. From 2012 to 2014, significant capex is being spent for phase 2B. Red chart is steam injection, and green chart is oil production, okay? So you could say, and we had this conversation with a friend, well, this probably was a mistake, right? But today, this company is getting acquired for $8.5 billion, so 7.5 in equity, $1 billion in debt, 8.5, 85 per flowing or so. So was it a mistake, right? So something to think about when you integrate facilities and you're able to generate that cash flow over the many, many years, there's value realization. And same, I think, applicable to solvent facility integration. Okay, when it comes to geology, obviously we have very different geologies, heterogeneities. What you want is basically the sandstone type of geology, which is oil sand. You want over 27% porosity, high permeability, so 6-7 Darcy. You want a very thick bitumen kind of slice, pay. But we do have sandy IHS. IHS stands for inclined hydrolytic stratifications. Soon I will show a picture of that. And they could have various geologies that's very complex. So steam chamber development could be hindered because of those. Okay. And this is a visual of those. So this will be injector producer. And here you have maybe IHS here. So imagine you inject steam, but you can't drain that oil. There's heat transfer, but there's no drainage. So what do you do, right? So we use control devices, different optimizations. Imagine now it's solvent. You need the coin back. You need the silver coin back. How do you operate this? One of the challenges. Another one, if you see from a broader point of view, you can have like a layer, right? So you really have to know how to kind of utilize this technology when you inject solvent and steam. And public enemy number one, right? So you have kind of complex geology, low thermal conductivity, can't really drain that oil. You're trying to develop that, but that geology could hinder the development. Okay, but maybe all of this is just in my head. Maybe nothing here is important, and why do you even care? 2022 world oil reserves, AER, look at Alberta, 9%. So we're the fourth one after Iran, Saudi Arabia, and Venezuela. Huge resource. 90% of that, over 90% is oil sands. 80% of that is what I'm talking about, is in situ. When it comes to production, huge producer, Alberta, again, 90% oil sands, over 90%, 80% is what we're talking about. Huge price. Okay. Sorry, this thing been, yeah, 80-20, mining and 80% in situ. So as we kind of develop our mining operations, right? All things you see at surface, in situ becomes more and more important over time. Okay, we hear a lot about tariffs, US relationship, what's going on with shipping. Canadian importance on US oil deliverability is even more important than ever, despite of what you hear on the news. We currently produce about 60% of the imports. Majority of it is through the oil, what I'm talking about. And some people say, okay, well, maybe they can use like Saudi oil or ship it through Texas somewhere. Well, most of this oil is going through Enbridge main line, 3 million barrels a day, right? To Midwest. And you don't really have a connection to Midwest from anywhere. And those facilities there, refining facilities designed to handle heavy sour, the oil that we produce. So in a way, there's lots of opportunity here for optimization and technology development. Okay, let's talk about Imperial, okay? So this is from their Imperial Coal Lake 2024 slides. It's explaining SAGD. SAGD stands for Solvent Assisted SAGD. It's exactly what I was talking about. You inject steam and solvent, there's co-injection. In their case, I'm not sure, it should be close to 10 vol%, and they tell us they inject diluent, okay? So we saw on the vapor pressure charts, hexane-pentane mixture diluent, and SIMD supported that. And then what happens, you transfer the heat by conduction, but the solvent provides that convective forces. So conduction and convection, solubility, which is the light green, and bitumen drainage by gravity. So that's what we're seeing. Continuous steady state injection, well placement identical to SAGD, lower GHG intensity, up to 40% reduction relative to CSS. So they utilize CSS, which is a cyclic steam process. Bitumen rate uplift and steam to air ratio reduction relative to SAGD technology. No material change in SAGD configuration, and that's one of the advantages in solvent utilization. Okay, so last year, and I'm gonna be giving lots of examples for other companies as well. Ramping up production to achieve 15,000 barrels a day, expected to reduce emissions intensity by 40%. So we see communication on the Grand Rapids project, SAGD. Okay, this year, first commercial application of SAGD. Okay, there were times I would show up, I will talk about solvents, people will be like, okay, whatever, sounds good, good story. And guess what? Production forecast for Mahican, that's how you guys say it? Mahican, yeah, it's good. The wedge is closing there on sustaining production, utilizing this technology, at least from the forecasts. Grand Rapids utilization also provides the sustaining production, and the type curve for projected production actually below what they estimated. So we're no longer talking about something experimental. These guys did a very good job commercializing this concept, and they talk about it. So something to be mindful of. Okay, so this is my work for ConocoPhillips, former ConocoPhillips employee, but I'll speak only to this chart without interpretation. What happened here, there is a mesh model, thermocouples, flow control device, right? Wet test meter. There is a little tray at the bottom. You inject different things, and you see what's going on at the drainage, right? A test. So assignee for this pattern is ConocoPhillips. The attempt here, optimization of steam and solvent injection, timing, and oil production. I think maybe they're seeing this. This is base case SAGD. This is methane, which is non-condensable. This is, I think, superheated methane. This is supercritical superheated butane, which is closer to the diluent stage. Uplift opportunity relatively to SAGD. Cool, eh? My peers, TJ Wheeler, collaborate, amazing mentor. Bo Chen was amazing simulation engineer from Houston. 5-meter configuration, injection production. Here the attempt was solvent and CG co-injection with tapered pressure. Again, we see injection of solvent, steam, chamber development. What happens next is intriguing. We commercialized in the industry the infill wells. Those happen to be in the tier between the two well pairs. You see those right there? that heat is being transferred. That's why infills work, because you can drain oil from that section. This is prior art. 2 chambers developing. Now they're coalescing. You see the teardrop shape. High pressure here, low pressure here. Movement of solvent. You get the silver coin back. And solvent return percentage, close to 100%, utilizing this process. Now, if you have a thief zone, which is a big problem for many producers, you kind of mitigate that as well. Let's say you have top water or top gas, you're able to do that. But what's the relative relationship between SAGD, ES-SAGD? So that will be enhanced SAGD, right? Enhanced solvent SAGD. You have a baseline, you have ES-SAGD, and then you can produce further oil. And obviously SOR, base case SAGD is here, closer to 3, ES-SAGD here, and you're able to, with the new process, reduce SOR even further. So that supports oil recovery scheme, solvent recovery. So lots of innovation in that space. MEG energy, right? MEG is in play. We saw Strathcona, Cenovus bidding on MEG. We talked a little bit about them going into the oil glut with expanding their facilities, but they're getting rewarded now. They do something similar, but with infill well. There's injector producer, infill well. Cold solvent systemically extracts heat from the hot reservoir rocks. We talked about vapor pressure. We're talking about propane here. And the idea here that if you're able to go inside that oil, you will produce diluted, asphaltene reduced, upgraded, metal abated, Daruma oil, okay? And this happens after achieving 30% recovery factor in SAGD. And the SOR in the chamber could be lower than of that of SAGD. So that's kind of the concept, utilize the infill. Now they actually did it, okay? And now we're gonna see results. So this is oil production in green and oil production decays, right? So C3 NCG co-injection, there were other patterns that they shared, but they were very close to that. So we don't see commercial implementation from MEG. What's really even more intriguing for me, and it's kind of closing to loop what I talked about when it comes to vapor pressure conditions, is that propane recovery in liquid phase was at the very bottom here. So is this more like a solvent or more like an NCG? And you have huge gas recovery here from this perspective, and it's over 100% because they're able to recycle it. So I think this is very intriguing. This is in the public domain. There's reference below, so take a look. But that explains maybe why they did not commercialize solvents. So not going to talk much about this. I led this program for Cenovus, solvent-driven process cumulative oil production, steam injection, SOR. You can basically see here how steam injection, you injected 180,000 tons prior in the 2 years, and then only 20,000 tons of steam. Huge reduction in CSOR, and you can see the oil production. I'm not sure exactly where it stands right now, but there was an attempt at Cenovus to try something from the solvent perspective area. SAP, early program here for SAP, solvent assisted process. When I was kind of getting introduced to this industry, started around that time frame, so my mentors were working on this. 785 barrels per day prior to SAP, 879 after, tried high pressure SAP, low pressure SAP, and you can see basically response in oil production rates. I think what's really important is that the cumulative SOR kept declining to 1.66 over the course of this time. High fluctuation in ISORs, but pretty good performance in CSOR. So that's solvent-assisted process. We'll talk a little bit about Suncor, hydrotreated makeup diluent being utilized around 2022, 10 volt% right here, using diluent. And I'm not exactly sure where it stands. I looked at the public data, but didn't see any recent kind of updates. But if you look at the KPIs, then it's very consistent, kind of reduce steam utilization, improve oil production, maybe upgrading. What's nice about them, they have access to their kind of downstream facilities in a sense to refine. So they're able to extract that as well. Conoco did something in this space as well with diluents. SOR reduction was 27% and 14%, but there's some language there about solvent recovery challenges. Small company called Conacher, 20,000 barrels per day, close to 20,000 right now. Higher bitumen production and recovery for SAGD plus, which is kind of, I say, ES-SAGD. Lower SOR, diluent blend ratio, GHG emission water consumption reduction. So that's kind of the attempt. I looked at the public domain data, no updates there. I assume they did not commercialize. Maybe oil rates are kind of challenging to do something in this space, right? So we talked a little bit about that as a background. PED 203W from December 2022. Okay, CNRL. So my understanding is that, and based on the language here, is the Kirby South, they did butane injection, and they saw a reduction of 45% in SOR and GHG intensity, and solvent recovery was 85. And now the attempt is to go to Kirby North for commercial scale solvent PET development at Kirby North. They do at Primrose steam flood area, solvent injection 2-year pilot program. But here they want the target SOR and GHG intensity reduction of 45% and recover solvent at 70% recovery factor. So everybody's doing something, right? Maybe there'll be a question, how can companies collaborate, which they do. But it seems like it's an active space. And we know the price is huge because if you're able to reduce the steam, you can maybe reallocate it. Maybe you can take GHG reduction. So that's an opportunity. But because of the scale of the resource and the operations, any optimization here is very meaningful, especially for a huge producer like CNRL. I think they produce 1.3, 1.4 million barrels a day. So globally is a huge player. But wait, there is more. Hanging Stone at Tabasco, and we're almost done. They utilized in purple line here gas injection rate, which is NCG, non-condensable, and cutting steam injection rate in red, and oil production is sustained. So pretty much everyone, if I'm not mistaken, try an NCG integration towards end of life because the cavern becomes very big. So you don't want to, by maintaining bottom hole pressure, you don't want to inject infinite amount of steam, and you want to reallocate it. You also don't want your SOR to go to the moon. So you mitigate that by cutting steam injection, NCG co-injection, and look at the SOR here going from level 6, 5 to closer to 3, 3.5. So those are meaningful cuts in the end of life. And so when we talked about previous work that I showed you, there's an opportunity here for kind of solvent recovery because anyway companies will inject NCGs. Okay, so what are the biggest challenges? So this is a WTI crude oil price NYMEX confidence intervals for next year, 2026. Sad news, guys, $60 oil. But a confidence interval could be 110 and maybe 30. So I'm dropping the mic at this point. Kind of unfortunate, right? I wish we had more confidence. But I think that's the challenge. How do you allocate capital, right? And we saw in the past where capital was allocated, and in the end, after a decade, you could monetize that. But again, companies are very busy now reducing debt, protecting the balance sheet, buybacks, dividends. We see some M&A. We saw Whitecap merging with Varen. Now we see Play on Meg. And so whoever wants to grow a little bit more, maybe kind of busy allocating capital, but what role does technology play in this environment, right? So this is more of a question, I guess, to the audience to provoke some kind of thoughts about this. Okay, so in summary, this is my last slide. The industry is phasing into solvent commercialization. C4, C5, C6. We saw Grand Rapids SAGD C5, C6, which is diluent. C4 butane attempts. My understanding, Kirby North could be next. Significant human and financial capital invested. I personally was co-pioneer at COSIA Pathways Solvent Consortia, collaborated with many of you. My understanding, just kind of doing rough math, we spent about 200 million, over 200 million is in industry. Could be closer to $500 million over the past 20 years on solvents. Emission reduction opportunity, based on everything I shared, is between 20 to 45%. Small asset integration for now, asset morphology matters, right? So we saw some huge assets, we saw smaller assets, but when I talk about Kirby, you can maybe do a pilot in Kirby South, then you commercialize in the pad Kirby North, and maybe you scale as you go from there. By the way, I'm not suggesting they're gonna do it, I'm just kind of speculating based on publicly shared slides. Modular integration for all assets. There's no scenario that I see here where we're saying, okay, here are the keys for SAGD, we're done, we're doing all solvents now. I don't see that at all, but I do see it as an extra kind of layer to reduce emissions and improve oil production. Significant collaboration at COSIA pathways. Growth possible with solvents. I think you can start thinking about it now. How is it possible? Well, if I'm able to reduce steam, I can deploy that steam without maybe building new facilities to generate that steam. And oil price volatility impacts implementation and advancement, and I think it's kind of a given based on everything I showed so far. Okay, so this is my email, alex@waterca.ca. Here's a cool picture. This is in the Christina Lake area where we have a pad for C&Q and a pad for Synovus. And if you think about one of them commercializing solvents, and remember we saw the picture downhole in the reservoirs, if one is operating higher pressure, one is lower. So lots of thoughts come to mind when you see something like this, but nevertheless, I hope you enjoyed this presentation and maybe you guys have some questions. Thank you.
Hi, my name is Roger Bernard. I'm with the Novel Hydrocarbon Extraction Group, and we'll be asking questions. So if you have one here in the audience, just hold on, we'll just give you the mic.
So after switch to the solvent injection, what's the steam temperature change different?
Yeah, so it's really a function of those vapor pressure curves and the mixture of what's being injected, okay? And for example, for propane at 3 MPa, it will be gaseous, let's say at maybe even 100 degrees. But then what's the impact of that convective effect, right? In the case of SAGD, you have diluent utilization and the vapor pressure curve is closer to the steam one. So you have to almost maintain the same steam injection rate to provide the enthalpy to vaporize the solvent, right? So I guess the answer here is depends. And so many people like me in the sector, like some people in this audience, looking at the science and modeling what's the optimization and how can you get more with utilizing less, right? Because less steam, less solvent, and more oil, less emissions is a positive for this process, right? So the answer is it depends. Current, it's a function of pressure, but I would say for 3 MPa, it could be as high as 240 degrees Celsius. Yeah. You don't have to, and that's the advantage. Yeah.
Sorry, people online won't be able to hear, so if you can repeat the question whenever it's asked.
So the question was, what's the, how much steam you can cut or what the temperature operating pressure is? Is that the question?
Yeah, if the temperature can reduce because of that, currently a lot of steam loss because the steam heat loss between the wellhead and the
Yeah, so we saw that at 150 degrees or so, the viscosity for oil, I would say, is closer to 10 centipoise, right? And then as you progress, but that's really like thinking about honey or maple syrup. If you microwave it, it will flow faster, right? If it's still very viscous, it will flow very slow. And it could hit on your economics if the flow is too slow because you could be injecting something, but you're not making any money, right? So all of those things would work together.
Great. For SAGD wells, we drill at a separation of 5 meters. Could we optimize it by changing the separation between the injector producer for solvent wells?
Yeah, and I think that's the next phase of completions. You could have outflow control device for steam, but maybe there is a better completion for different solvents. Same with the inflow devices. Maybe the spacing could be optimized as well. But it's not always 5 meters, you know. Companies use a technology called MWD to drill. And I think that's kind of the standard, I would say. At least from all the slides we saw very similar language. But I think it's an opportunity to optimize further. To be mindful also of the pay, because if you increase that spacing and you pay 17 meters, well, now you need communication of 10 meters, let's say, but then your chamber is like 7 meters, right? So that doesn't sound like something that makes sense. Also, that's right. Also, if it's very gassy, you don't want to be too close to the producer because you need to create a layer of a subcool to control that the solvent doesn't short circuit and goes to the reservoir to develop the chamber, right? So there's lots of dynamics here.
Hi. As you have pointed out, solvents do reduce the SOR, and as a result, a major option there is to reallocate the steam to another pad or new pad on the development. So as long as it's profitable to do so, an implication would be that a project would continue to use the same amount of steam as it did before the solvent injection. And so you really wouldn't see, you'd see a reduction in intensity, but there would be no reduction in actual emissions. So with that in mind, and if operators do continue to work like that, and they do, their behavior has indicated it so far, could it be that you have to wait until the next generation of new greenfield opportunities, such as the Ebert development by Imperial and Suncor, where you're implementing solvents from time zero to really see a substantial reduction in emissions from these projects?
Yeah. So there are two angles to that. The statement I made was an opportunity to do something, a scenario, right? But you could take a steam cut. For example, if you co-inject NCG, we used the hanging stone as an example, towards end life, there is no doubt the steam is being reduced. Now you could, for their case, they have 25 well pairs and they drilled maybe like 2 over 10 years. So they didn't really introduce new well pairs until recently. And so in that specific case, there was a legit steam cut without reallocation until the next phase of wells came in. So I think it's really important to be mindful of that because companies will decide what the strategy is. But in the case of greenfield expansion, I think all these learnings and what we saw with SAGD, it provides an opportunity to permanently reduce enthalpy, right, steam utilization. But in their case, it also could be that you need to transfer that heat to vaporize the solvent, right, because it plays 2 roles. So I'm not sure exactly how they're going to approach this.
Another question?
Is it?
Yeah, I recognize not everyone's going to be able to use maximum steam capacity unless it can, but there are other factors.
Also, there was lots of efforts to heat the solvent at surface, right? So we're talking about technologies like direct heating, electromagnetic heating opportunity, but it's still in the early technology development stages, my understanding. But assuming you need like less enthalpy, it provides this opportunity to maybe vaporize solvents without steam co-injection. I'm not suggesting this is commercial at this point, but it's kind of, we could look forward to that as well.
I've been in 2 presentations in the past year at CHOA Connects and slugging it out, in which the two companies you cited in terms of CNRL at Kirby and Imperial Oil at the Grand Rapids project, both companies have indicated, and I wrote it down so I remember this, that they saw their process as an acceleration process. CNRL in particular indicated that the injection of solvent at Kirby was not improving their rate at all. It keeps the rate flat, but that was a good thing because the SOR is down and that allowed them to allocate steam to new pads. So their overall project production was up, but their overall SOR was going to stay the same.
So then you don't grow the emission output, I guess, right?
Well, you don't grow it, but you don't reduce it. But I just thought it was an interesting. That's the first time I'd heard companies come out and say, these are acceleration. It's an acceleration technology, or at least the way that they're viewing it, rather than an incremental recovery.
Well, for sure, we saw it in the Grand Rapids slide where the forecast was overachieved. Yeah. So.
We've got some questions from
Yeah, there's a
online.
We have a few questions online. So have you looked at injecting non-condensable gas like CO2? Also, any takes on alternating between steam and solvent injection instead of co-injecting together?
Yeah, so there was a pilot injecting CO2. I was involved in this pilot. So industry tried that. It's in the public domain. Clearly, nobody's doing it commercially, so that speaks to something. I think one of the challenges is the vapor pressure conditions, right? There's a reason why for CCS, my understanding, we have to go 1,000 meters underground for 10 MPa to liquefy that CO2 so it can be stored. The alternate process was simulated in the past. I saw studies, I think this process called SAS, S-A-S, so cyclic steam solvent, and it showed some promise, but only in simulations. What's interesting about this question, and I'm sure companies thinking about that, is the main advantages of SAGD versus CSS that it's not cyclical, it's continuous. So you continuously inject and produce and able to do that. And so there will have to be an incremental benefit to inject that solvent and produce it. But we do see some companies doing like steam flood experiments and co-injecting solvents. So it's a thing, cyclically, yeah.
Okay.
But not in SAGD.
And what is the ratio of solvent and steam?
So from those examples I shared, we saw as from 10 volt% to as high as 90 in some examples.
Okay.
So
and
there
last
were attempts
question.
to really do like the Roger Butler Vapex, but kind of scavenging that heat in situ to vaporize that solvent so it can grow the chamber, yeah.
And any thoughts about using nitrogen or CO2 as nanobubbles to get better extraction with minimizing the amount of energy in GHG?
Yeah, maybe companies will try it in the future. I'm not sure. But the vapor pressure conditions suggest maybe it's not a great idea, yeah.
I've got a question here.
I think it's more of like this using the solvent is acceleration of the oil that we get from the ground. And maybe that's more up to the like cyclic perspective. If we inject solvent for a few years and then stop that and it goes back to SAGD, then we are going to, because like more oil has been produced, we still need that amount of heat to heat up the reservoir. Is it just delayed the amount of cumulative solvent steam that we're going to inject it?
Yeah, so that's a very good question. And that speaks to that solubility effect, right? So whether it's just conduction and you add another thing that just conducts heat, or you have those convective forces, right? One way to verify that if you have solubility is really improvement in API, right? And then measuring the material balance between what you produce and the solvent and liquid phase to quantify it. So industry is fairly advanced in understanding those dynamics, using reservoir simulators, using real field data, doing C7 plus test and from the gas side, SIMDIS from the liquid side, to say, do we produce more or less? And in some of my slides, there were some extreme efforts to cut steam to basically almost zero. And then you basically have a simulation case and you say, okay, but I'm still producing oil. What is that dynamic? Like, why is this happening, right? And because of COSIA Pathways collaboration, companies are able to share this information. And maybe that's why we see commercial cases at this point.
Thank you for the presentation. You covered how much industry has invested in this technology. Do you have evidence of return on investment?
Well, excellent question. I think it's kind of like asking return on SAGD from 1978 to 1998, utilizing government UTF project. So what happened in UTF, underground test facility, there were 2 wells placed to test whether SAGD is going to work. So today, what we see today is remarkable. It's like a miracle, right? 1.7 million barrels a day, royalties, taxes being paid, returned to Alberta. So I don't even know how to answer that, because if this technology has this opportunity to be what it could be, in your case, maybe not even increasing steam in the future, right? Then very difficult to quantify that return on investment. But I'll tell you one thing. From when I started my career, We always worked on reducing SOR, always. There were always projects like different steam kind of allocation, completions, strategies, NCGs, pumps, and all of those things work together. So I think solvent is just another add-on to that.
But at company level, say Christina Lake,
Oh, I can't comment on the
there's
company.
no public data on return on investment yet?
I'm not sure.
Okay,
Yeah.
thank you.
Yeah.
Just
Well,
go.
for commercial SAGD, we can take the delta between the type curves, look at the oil rate for WCS, and incrementally say, well, we produce that much extra, right, for that scenario. So that will be fairly easy to do.
I've got a couple of other questions, and then we'll be wrapping up. At what CO2 price do solvents make sense as a way to reduce GHG emissions?
Yeah. So I saw that question. I'm not sure about the answer, right? Because it depends. Because in my view, there are lots of tools in the toolbox right now with NCG, with timing, with reducing bottom hole pressure, right? But then if you have, let's say, bottom water and you have inflow of water, then it hinders your operations. So it will have to compete economically, I guess, right? For that penalty, I guess, for CO2 price increasing and whatever you want to advance or how you would operate. But like in any business decision, I'm sure companies looking at different scenarios and saying, if this happens, we do this. If, you know, but I'm not sure if solvents is the path.
I have one last question. How important is it for the reservoir to have the right solvent for the right reservoir? Is there a difference between using butane or diluent or
huge
propane?
difference, right? And it's really a function of like, if you inject NCG, it's gassy, so then you can cut steam significantly, but it's not soluble. You could also have reservoirs that are fairly shallow, so you cannot exceed certain bottom hole pressures. So you have to operate at those conditions, and those conditions will have to meet the vapor pressure conditions of the solvent. To your comment about Ebert, right? I think that you mentioned. So that's very unique opportunity there at lower pressure environment. So again, it depends. And that's why the science is so intriguing. Like, what do you use? How do you utilize that? What the optimization strategy you use? And then everything here we talked about requires significant amount of investment from facilities point of view, because now you need to recover the solvent, you need to cool it back, separate, re-inject, right? Downstream, you're going to have that solvent as part of the flow in the pipeline as part of the diluent if you already produced it. Maybe you don't need as much diluent that you buy later on. So lots of dynamics taking place here. But it's very unique to each company, for sure.
In terms of recovery, in terms of economics, in terms of all the various
And the reason
competing
why,
parties.
they're also geographically in very different locations, have very different pace, very different geology conditions, like different heterogeneities. So they have to be very mindful of that, for sure.
Well, I'd like to thank Alex for a fantastic presentation. I think it's one of the highest attended events that we've had in quite some time. So appreciate everyone making it out. And the whole point of this is for networking. We have another half an hour here just to network here in the audience. But again, a round of applause for Alex, and thank you very much.